Hello everyone, welcome back to Course Edit. So today we are going to do some question practice. Basically, we'll be solving few data structure and algorithm questions. So depending on how much time we are left with, we'll be calling it a day. So basically, we'll be learning for 40 to or maybe from 30 to 60 minutes. So let's go with the first question. So your first question is, it's basically a graph question. I would say it basically includes DFS graph and all. So let's call it the critical network. The critical network for your question. So let's start with the question. So suppose you are given with, so you have two inputs. First is your, you are given with, so you are given with an undirected graph. Let's call it network, or let's not write it like this. So basically, so you have an undirected network. You have an undirected network. Network of n cities, and your m roads. So you have this undirect network of n cities and m roads. So each road has a construction cost. So each road has a construction cost. So you have, however, so however the government has a strange requirement. So let's talk about the requirements right now. So let's talk about the requirements. So first requirement is basically your the final networks must connect every city while connecting the minimum possible total construction cost. So basically you're given some cost with which you have to create this all this stuff, and the final network must connect every cities and your basically every cities in your this country or whatever state you are living in. So it should connect every city while using the minimum possible total construction cost. Construction cost. And second thing that you have to do, this is an additional condition, you can say additional condition. So let's write it second only. So if removing a road, so if you're trying to remove a road from the final network, so what you have to do, it disconnects. So it disconnects the network that so if it disconnects with the network, that road is actually called your critical road or whatever you want to call it. So it's critical, right? So let me read the question again. So for the critical network, you have an undirected network of, sorry, this is the topic of the question. So you have an undirected network of n cities and m roads. Each road has a construction cost. However, the government has a strange requirement, has two strange requirements. So the final network must connect every cities while using the minimum possible total construction cost. If removing a road from the final network disconnects the network, that means that road is called critical. So your task is to find, so first your task is your task. So you have 3 tasks, or you can say you have one final task, which is your output. So first task you should do is that construct the minimum cost connected network. And second you have your find the number of critical routes. Find the number of critical routes or roads, you can say roads in that network. I think I've chosen the wrong that formatting. Okay, so this was supposed to go like this. I'm so sorry, I might have written everything so small. So wait a second. Yes, so third task you have your output the critical roads. So you have to output the critical roads which are present over there. So let me give you some input. So let's say we have this as the input. So example input, you can say. So n equals 6, m equals 9. And obviously the roads or the graph, you can say, are basically like this. So 0, 1 and 4. So 0, 2 and 3. And obviously you'll have 1, 2 and 2, then 1 with 3, then 5, then 2, 3, 7. Then you have your 2, 4, 8. And obviously you have your 3, 4, 6. Don't worry, I'll be explaining this input as well. So this you have 4, 5 and 10. So these are basically your roads which you'll be constructing on every this city. So what each road is. So obviously now you know that first you have U and V and last is your K, or you can say cost. So this is your first node from which it generates or starts. Then you have this ending node where the road ends, and this is your cost of construction, which you have to like in how much amount you have to create the road. So obviously you can find the critical roads as well. So expected output, let me write it over here, or let me write it over here only. So expected output. So the output is expected to be this. Suppose let's say you have this critical roads. Well, you can write this, or maybe you can leave this as well. Since you have to check, you don't have to worry about what you are writing. So you have this 1, 2, 0, 2, and then 1, 3, then 3, 4, and then 3, 5. So let's begin with the explanation of the question. So you have your undirected network of n cities. So let's create some. So let's create few diagrams. So, or we can just begin with the explanation, and then we can create it in between. So obviously, the problem looks like it requires two completely different graph algorithms, which are your MST, basically minimal spanning tree, and second you have your Kruskal plus DSU, which you can derive from. Basically, we studied Kruskal, and then we studied these two as well. So basically, these two you need, right? So obviously, how do we obtain the minimum cost connected graph? We have to first think about that. So to think that we have an MST, which is your minimum spanning tree. Since we are given that, that each undirected network of n cities and m roads is there, and each road has a construction cost, which the government has two final requirements. The final network must connect every cities while using the minimum possible total construction cost. So just if we have to just connect with all the cities, then we don't need to like connect everywhere. So suppose if this is a city A and this is a city B, this is a city C. So it is never said that you have to minimize the cost of petrol. It is said that you have to minimize the cost of construction. So obviously you won't be bridging B and C as well. Or if there is a bridge which is such as you have for B and C, which is suppose you have one and here you have two and here you have three. Then obviously you'll be creating A, B and C road, not this one. And suppose if this was one as well, then you would have created B, C and A instead of creating A, B, C. So this is what you would have created. So that's what we have to just minimize. So by this graph, by this diagram, you already know that we have to use MST and Kruskal DSU. So that algorithm will be very helpful. This is your Kruskal's algorithm. So we don't need every graph. So we'll be just using a minimum spanning tree. So we'll be just creating an algorithm which helps us with that. So for those who don't know what minimum spanning tree is, obviously I can tell you. So suppose you have this A, B, C, and then you have D and E. And suppose you have this. And obviously if you want to remove C and D, then you'll have, it separates the tree into two components, obviously. So it'll be like A, B, and then it'll be like C, D, and then obviously since you are removing C and D, so you might connect this as well, A to E, but you can't do that because C is not present. So it'll actually create three components. So that's the reason every branch is important in this minimum spanning tree. So that's all for the explanation, I would say. So let's construct the MST for our this whatever we have over here. So either we can do it over here or we can just directly write the code. So I would recommend writing the code along with me, or you can first write yourself. So you can go to that lecture where we have studied MST and all. Then you can come back to this question and then you can solve it directly over here. So let's begin with the code. So let's create some edges, I would say. Extract edge, basically this. And you can just have int u. So we have cost, u and v. So we have all this. Let's say we have your DSU over here. So you can create this class of DSU if you want. So you can just write parent as there and some. So basically you don't have to actually create this class again and again. So that's the reason we are just directly creating a DSU class, and then we will just directly implement that DSU construction directly inside this. So basically we'll just need single class for that, and I mean you're getting it right. Vector and rank. Then we can go with your DSU. Let's say we have this. Oh god. So actually mic was directly on my face, so I was unable to see the keywords. And obviously I'm not that good at blind typing, I would say. So obviously you can resize your rank, or basically we will be resizing it because for every different input we'll need this. So instead of taking n over here, we can just directly resize it from this place. So basically resize just gives you the size of your rank this. So either you do like this vector int rank n. So either you can do this or you can do this rank dot resize. I mean, first you'll obviously have to create a vector int rank. Then you'll have your rank dot resize. So I'll be just adding this as a comment over here so that you don't have to search anywhere what this means, even if you forget, obviously. So this we have done. Let's create our second basically function, which will be your, I think we need a find function, and then we can just create a, then we can just create our unite function and all the functions which you need. So obviously you know how to find, right, in your MSU. So you have this, then you can just apply your if this. So why do we do this? So suppose if the parent is the same, then that means we can just return it itself. And suppose if the parent was something else, then we can just find it over here. Return parent. Basically, it's just the traversal, you can say that. But this traversal is much better than any other traversal, I would say. Obviously, it works only for your MST, for Kruskal's algorithm. I mean, it just doesn't work for just Kruskal's algorithm, but majorly it's made for that only. I mean, they just look very good together. Oh, sorry. So this would be, sorry, I did mistake over there. And next you can just use bool unite function. So basically unite just tells you whether you want to add two of those branches or not. So by that what I mean is, let's say we have this distinct set union, disjoint set union. So let's say we have A and B. So do you want to combine these sets? Obviously it will create a combination which will be from A to B. Basically it will give it an edge. And if you don't want to unite them, then you can just leave it that you don't want to unite them. So the main logic will go over here in the unite function. So basically this was the same for now. And obviously in the unite function you won't change much. You'll be just checking whether it just helps with the costing or not. Or we can just check that directly afterwards in our basically you can either write the logic over here in unite function, or you can create a different methodology in main function where you can just do it in the main function as well. You can just write the logic over there as well. So I think I should be doing in the main as well, because let's keep the DSU as it is in every case, and then we can just implement the logic separately in the main function for every question whichever we are going to face. So obviously you need to have two of the, I would say, nodes. Let's say they are int A and int B. So for these two nodes, you can just have your whether they exist or not. First, you have to find that as well. Find A, then B equals to find B. So basically, it will go and check every node which is superior to it, and it will find B in that. So we'll be just replacing B with that B. So that superior will just conclude that this can come under me. So, or this is under that, A and B are under the same that tree, you can say, the superior, which I told you, and that superior will just allow them to unite. So let's say if A double equals 0, return false, and if rank. So if rank is your So if rank A is less than rank B, then what you can do, then you can just swap them. So basically this is same from the MST class, minimum spanning tree. I don't know why it took an extra space over there. So don't worry about that. So we are just so we can just assign a parent now to your that minimum one. So if this would have been so we are swapping because suppose if A was greater than B, then we can just apply that to that your parent is basically parent of B is your A. And let's say if this was not like that, then we won't swap, and that will still just give us what we need. So it's like killing two birds with a single stone. Otherwise we would have to write two different things. And suppose if you get something like this, then you can just say rank A++. Obviously we'll be increasing the rank if we find similar this ranks with the A and B, so that this rank of A can increase, because we are taking that rank of A is less than rank of B, then we are swapping them so that our A stays above that B, and then we are assigning B to A. And here we are just checking whether if the rank is equal, then we just assign it a greater rank. So basically A is your greater rank and B is your smaller rank, so we have to just assign A with the greater authority and B with the lesser authority. So construction of our DSU is complete, I think. Let me check if okay, so we didn't return any last true or false or anything else. Okay, so we have returned false over here, but we also need to return true right over here. So after this, we are complete with our DSU function, or you can say DSU class. So next, what you can do? Okay, so wait, I just saw this. We are missing a semicolon. So that's what we need, I would say. Okay, so we missed a semicolon over here as well. Okay, so that's it. So now it's time to write the main function over here. So in the main function, we'll be just taking few inputs. Let's say int n, c in your n. So console input n. Then we can just have vector of edge. Sorry, vector of edge. And then we can just name it graph, I think. Let's call them. Okay, so let's call it graph only. Or we can call it a network, which our question originally had. So basically your network is, let's say it's of size n. Then we can have your, this, what do we say? We can just take your input for int I equals 0, I less than I plus plus. Obviously plus plus I is better than I plus plus, because I've already told you in the research segment of our channel, I would say. So this is basically 1 byte slower, not 1 byte, but like 1/10 of a byte slower than your plus plus I, because here you have to copy this in a separate that memory, and then you can just take back from that separate memory and you just add this. You just replace your I with the next integer afterwards. So basically it's like 2 memory required for a single thing, so it will just not be efficient for your memory optimization, I would say. Next we can just have your input. Let's say we have network dot, so let me just check what we took, u, v and cost. So network dot u is equal to your let's say, okay, so we have to take input as well, or we can just directly do it like this, c in network dot u. Well, basically you can assign them later, or you can just directly do it over here. I think it'll work. Let's network dot v. Okay, so this should work. So we have your network UV. Oh, sorry, this was your cost, not V. So we have this. So next we let me check what we had to do. So basically the final network must connect every cities while using the minimum possible total construction cost. Okay, so basically we'll be just taking that cost in our consideration, and we'll be just doing everything according to the cost. So at first we can just either sort this complete vector, I would say. So let's say we have this network dot. So we have this network dot beacon dot end. Okay, so for some reason I was unable to see B as well right now. No worry about that. Actually, the mic is on my face, so I'm having much more problem than instead of. So if you know this function that we can just directly assign in the in place of comparator, then it's well and good. Otherwise, you can just write that in the comment that you don't know, and I will be providing the code for the separate comparator over here. So bool comparator, we can just write this comparator, and then we can do it over here as well. Pass, I would say. So let's see, you have this edge A. Okay, so since we have to like do it for everything, so we can just use and as well. Basically this ampersand symbols tells you that you have to change it directly where it is stored. So you have this edge ampersand A, then you have your edge ampersand B. I don't think we have anything else. Yes, so we don't have anything else right now. Next we can just return this, I think. Return A less than B. Sorry, not A less than B. A dot cost less than B dot cost. Basically we have to solve this according to our this costing, and we have to just assemble it from lower to above. Basically you're getting it right, from smallest to largest according to the cost. So I think this looks good right now. You can obviously just write this edge ampersand A comma edge ampersand B. Then you can just assign everything. Basically a dot cost sorry, return a dot cost less than a dot sorry b dot cost. I don't know what's happening right now. So use this only when you don't know. Use it instead of direct function. Insert if. So we can just replace it by this comparator. Let's call this comparator. Okay, so let's leave it as that only. Then we can construct our object. So this will be your first object, I would say. So let's create an instance for that. Actually, the instance is automatically created over here. So we have created the object above over here, and then we just created an instance named this DSU. So let's say the total cost is required to be int total cost that's required is your 0. For now, it's not required. Basically, we are just getting the total cost as 0, and we'll be just pushing it according to our cost, which we are going to get from there. So let's go with this vector edge. Then what do we have to calculate? Okay, so let's call it minimum spanning tree right now, and then we can just go with the for loop for auto edges sorry edge to edges Uh, we can just have f dsu this s dot u less than s dot v. Sorry, we have to pass this. We don't have to check that right now. So we have this mst dot pushback. We can push the edge according to this boolean this unite function. Yes, so we are uniting this, and if we have to unite, then we can just push back this mst. We'll be just adding that edge over there. So basically that edge will add everything. Yes, it looks good to me. Oh yes, I forgot one thing. We can just write the total cost. We can do it separately as well, but let's do it over here directly, so we don't have to write the code again. Plus equals to your edge dot cost. So basically you can just do this again for auto edges as to mst. Then in mst you can just do this total cost plus equals to s dot cost. But that is unnecessary. For that you'll have to just travel one more time. So basically if you are just building that for your, what do we say, for your that project, then you'll obviously try to minimize the time, even if it's 0.0001 millisecond, I would say. So it's basically 10 to the power minus 6 seconds. So if it is even that much slower than faster than your actual algorithm, you will actually want to put that instead of putting instead of using that older algorithm which you built. So I would recommend you to try writing the codes which are most efficient. This is also not most efficient code. Basically it does not provide this plus plus I, and then we are just instead of directly calling it from this edge, we are actually creating a different memory space to just call this. So that is all like a different matter for now, but we are since just doing for data structures and algorithm, then it's fine, I would say. Then you can just see out this critical. How do we have to do that? Yes, critical roads, I would say. Let's provide this with this. Then we can go with for auto edge. Let's copy this directly. And then we can just have your edges replaced with mst, and you can have your cout. And basically we're gonna have this edge.u, edge.v, and we have this, sorry, it was supposed to be, yes, it looks good. I thought I wrote edges instead of edge. So where did it go? For some reason, after pressing enter, it just automatically goes up, as you can see. So I can do that while speaking as well. So if I like press this enter, then so I press shift enter instead of pressing enter. So if I press enter, it just goes up. So basically this is a problem in your Google Colab which you'll face. If you are not using the complete, I would say, this screen. So if you're using it separately, then you'll have to face few problems as well. So I think we are good with this, and let's return this z. Okay, so we don't need to return 0 because it all looks good. So there are a few problems. So okay, so it took network over here instead of edges. Let's just replace this. We have 1, 2, 3, 4, 5 replaces. Sorry, 6 replaces. And over here we have only 1 replace. So we have to just return this. Yes, so finally it looks good. So this unite function doesn't work, or what happened? Network.u.v.cost. So u what has no member named your u, I would say. Wait. Wow. Let me just think what the problem is. Vector edge. Then you have your network. Then your network doesn't have that. Okay. Okay. So suppose I have a network and I call an edge from there. So that is like vector dot edge dot, sorry, the component in that edge. So when I was calling this edge inside the network, it called this edge, and we had this dot u, edge dot u. Okay, so sorry. So we'll have to call our edge instead of directly calling dot u, I would say. So it doesn't directly have a member named dot u in this network. So it will be like vector dot wait. So for instead of doing this, we can just directly do this as well. For auto and ampersand edge as to network. So actually we can do it like this as well, but I actually don't want to waste time. So we can just see in edge dot u, edge dot v, and then edge dot cost. We just had to write network I instead of just directly doing network dot u, but I thought this would be okay. So let me write it that way only. Let me just do it both the ways, so you don't face any problem over there. Okay, so DSU n is not declared, or what? Let's replace it with 0 as well, so everything stays 0. Everything looks good to me. So what the error was, so if this end is private and the declared private here. Oh, sorry. So we actually declared everything private. By default, I think it's private, or what? So this is your public, I would say this. So DSU int is private within this context. Okay, so finally it's public. Okay, so we need to provide few inputs. Let me write the input over here first. So let's say 6, 9, and then we'll have your 0, 1, 4. Then we'll have 0, 2, 3. Then we'll have your 1, 2, 2, 1, 3, and 5. 2, 3, and 7. 2, 4, and 8. And we'll also have 3, 4, 6. Then we'll have your 3, 4, 6, 3, 5, 9. Sorry, 9. Then we have your 4, 5, and 10. So this should be like everything we need. Control C and Control V and press enter. Okay, so what the CNN. So our n was 6. We didn't take any input for m, I would say. Okay, so I got it now. And then m, and let's call this m. This would be your m instead of, sorry, this will be your n only. This would be your, okay, so let's remove this. Basically I tried to produce this for only n this. So let's do with the end method only. I equals to 0, I less than n, I plus plus. Then we can go with what was the name, network I dot m, network I, so this would be like less than m. So let's write everything at first. C in network I. Okay, let me just copy this over here. Dot u dot v dot cost. We have all this. Wow, I don't know why I did this. Okay, so this is having problem in itself. Let's delete this one. Let's delete, actually instead of deleting, let's press enter. Then you can have your add code. Then you can just do dot slash main, and that will ask, oh sorry, this function. And then it will ask for your input, which you can just directly paste over here. Corrupted top size, okay. So we have this 0 and 4. Let's say we have network I dot u, network I dot v, network I dot cost. So let me just debug this and then come back to you, because it's already 41 minutes past. Or let's debug this question till the time we are not able to get this, and that will also tell you how much time it takes to debug this whatever it is. So basically I'm teaching, so I'm unable to properly debug it right now, but yes. So basically these all functions are correct. We just have your problem in this input, I would say. So we have this 6 and 9, and we just need 9 sizes. 1, 2, 3, 4, 5, 6, 7, 8, 9. So what is the problem? Let me try that again. I believe that it is taking a single input for a single line, but let's try that as well. Let's do this. Let's save this first, then let's run this. Okay, so actually the internet is fluctuating a bit, or I don't know what's happening. Let me just do everything again. So we have this, and we have your input. It should be like 9 times 3, which will be your 27. So let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So there are 27 inputs, but it's saying that it's corrupted top size. So let's just go over here and let's see whether we have resized everything correctly or not. So we have this as well. Wait. So we have your n nodes. Okay, so sorry, it was actually my fault, I would say. Let's run this again. So we have this. Or wait, what we are pushing actually? We are pushing. Okay, so we took it like that of the graph, so it was actually giving us few problems. Okay, so now we are left with only one thing. Dot resize n, and did we pass? Okay, so we have to pass m instead of n in DSU. Where's your DSU? Oh, so let's pass M over here. So basically we didn't need this 6 right now because the way we took our this edge, we didn't need any N to begin with. Let me just copy. Okay, so this was I think already copied. So we are still getting a wrong answer. Let me just debug this again. I hope the parent is getting created. It's not like it has to be in private, right? It shouldn't be like that because that would be absurd to begin with, I would say. Okay, so we are still getting critical roads as nothing. So actually, according to our DSC logic, we are not getting any edges as your true for some reason. So I would love to like write this. Let's change this to this and then okay, sorry, where is it? So let's write it over here, then we can just have your cout false. Okay, so instead of returning first, we have to first print the output in your console. False, I would say. This will tell us whether everything is getting false or what is happening with our code, I would say. And it will also tell us whether it is actually getting getting inside this or not. Okay, so we are getting everything as false, as you can see. So our logic is basically wrong, I would say. So at first we have this. I would also like to print this as well, this network, because I feel like we are definitely getting some problem from there. Auto then we can just have your cout x. So basically if one gets cout, then everything gets cout. So let's run this again. Okay, so let's see what we got. So we have your 0011223334. So 00112223 and 4. Oh, sorry, 4 and 4. I actually can't see last 4 for some reason. Okay, so this was supposed to be m plus 1, I would say. Okay. Then we can go with your wait, what? I'm actually taking just from 0 to m, right? Okay, so we have to get m locations. So tell m it will create. So let's just check it directly. Why waste our time? Oh, so we got 0 at last. That means we are having some problem, I would say. Okay, so let me just debug it first, then come back to you so that it doesn't waste much of your time. Okay, so I actually got the problem. So it was like this. In DSU, we never took your parent as that input, I would say. So yes, we are just having, like, we can either do this, or we can just create everything of 0 size. So instead of doing this, so basically your parent has to be like your this first thing which you have to create. So that's the reason we're getting everything wrong. So now we can actually solve it accordingly. So DSUN, I would say. Then you have all this. Then you can just have your int I equals 0, I less than n, I plus plus, and your parent I equals to your I. So I think this should be good. So let's try it one more time. Okay, so we got it finally. So yes, as you can see, first one was true. Basically, obviously you have to include the first one. It will always be true. Then you have to like go with the other stuff. I mean, it won't always be true unless and until you have a critical road assigned to it. Basically what I mean is, suppose it was like 0, 1 and 100. Let's do that over here. 100 over here. And this was just 3 and all. But since you can see that we haven't connected any 1 to 0, but we have already, and also we have not connected anything from 1. So it will actually take 100 as well because of our given this code. Basically it depends on the input how your output will be. Actually I forgot to check the output for some reason. Okay, so the cost state 47. Okay, so this was the cost for the tree. Basically this 0, 100, which is your true. So basically this was the cost for your I would say this, whatever we needed. So this was your 1, 2, which was your critical road. Basically it is not the cost for your complete construction, I would say. It is the cost for your critical roads which we have constructed. So you finally got 2 plus 5, which is your 7, 6 as your 13, then you have 7, 20, 28, then you have this as your 37, then you have 47. Yes, so it is your complete 47, and you have your critical roads as well. So thank you everyone, thank you for joining today. Let's meet for the next Q&A session. Sorry, not Q&A, question practice session, where we'll be solving few more questions. So I think it will be I've already told you that we'll be having a fun session in your Python matplotlib, where we'll be designing a car. Basically we'll be animating a car using math equations. Animating car using math equations, using math equations in matplotlib. So that's it for today. So let's meet in the next video, and let's continue with that as well. Thank you everyone, thank you for joining. Bye bye.